Hello students, today we will try to understand forced convection. Convection in general terms is a heat transfer mechanism in which heat transfer takes place due to the motion of bulk of the fluid. You can experience this in daily life on a cold and a very hot summer. The temperature of the room although doesn't drop when you switch on the fan, but due to the motion of fluid a cooling effect is felt. This is nothing but the effect of convection that you feel which relieves you from the hot summer. The equation that governs this type of mechanism is known as Newton's law of cooling. Let me explain it to you step by step. If Q is the rate of heat transfer, it is directly proportional to the area. If the area will be large, the heat transfer will be more. And when the temperature will be temperature different between the surface and the ambient is higher, then a more higher cooling effect will be felt. You can you can relate to it uh, in such a way that when AC is running in your room and then fan is also running, then you feel more cooling effect because the temperature of the fluid has also dropped. So what we see now that there must be a constant here, and this constant is known as convective heat transfer coefficient. And although the geometry of the system and the area may change, but the main problem over here in these kind of problems related to force transfer or convective heat transfer is to find the value of H. One important thing is that at the surface where the fluid is in direct contact with the solid, conduction takes place because there is it is a sort of a bridge between this convective effect, and so when we equate this conduction value to this convective heat transfer value, we get a equivalent heat transfer coefficient. So if you know the temperature profile at the surface, then we can easily use the value of convective heat transfer of fluid and get this H value. There are two cases here. One case is where the fluid is being heated, and another case is where the fluid is being cooled. And you can see the curvature at the surface of this solid. One has a negative curvature, another has a positive curvature. So when you put this curvature or this the temperature profile in the conductive heat transfer equation, then you will get to know in which case the heat transfer is from the surface towards the liquid, towards the bulk of the liquid, and from the bulk of the liquid towards the surface. This being the case where the heat transfer is towards the fluid, and this being the case where the fluid is being cooled. There are four type of convective heat transfer mechanism, you can say. One that we are studying today, this is forced convection. Another is known as free convection, where the no external agency is required for the flow. The flow automatically happens because of a property which is the thermal expansion of liquid, where the because of the change in density the flow takes place. These are density driven flows, and this is very common when you make your tea or something. Then this is known as boiling, and another one is condensation. Why I'm telling you this? Because I want to give you an idea about the range of convective heat transfer. So in free convection we have the least amount of convective heat transfer, you can see here. And for forced convection we have the intermediate values, and for boiling and condensation these values are highest. And you may see, and you can find that in case where the fluid is liquid rather than gases, the convective heat transfer coefficient is higher. So this is something we can take away from this slide, and we can think about it. So because the flow happens in some regimes, and these regimes is dictated by a number known as Reynolds number, and after some when the flow has taken some critical value, the regime changes from laminar to turbulent. And we already know, for some reason, because of lot of mixing that happens in the turbulent region, the heat transfer coefficient there is higher. Don't take my word, I will show you some graphs that will prove this point. See, these are the two profiles, laminar and turbulent. And you see that the velocity profile at the surface, that is very steep for turbulent regions. And due to this, the shear stress at the surface is higher. And there is something known as the Colburn analogy that clearly shows that the friction that happens in the fluid flow is has some sort of an analogy with the convective heat transfer coefficient. And you can see this here in this plot that when the flow is laminar, the convective heat transfer value, although it drops, but it has some less value. But when this regime changes to turbulent, the heat transfer coefficient is very high. So when we have to make some theoretical calculation, we need to first find whether the flow is in laminar region or in turbulent region. That is a very preliminary calculation that we have to do. So these are the non-dimensional numbers that are important for force convection. This is Prandtl number. Prandtl number is the ratio of molecular diffusion of momentum to molecular diffusion of heat. This gives a very good idea about the thickness of the thermal to the hydrodynamic boundary layer. It is given by mu Cp by K. This is Reynolds number. It is a ratio of inertia force to the viscous force. This numbers gives us an idea that okay, in which region or in which regime our flow is happening. And the third number that is very important for convection, that is Nusselt number. Nusselt number, or Nusselt number as it's called, is the ratio of convective heat transfer to conductive heat transfer, and it gives an idea that how much convection or how much the bulk flow of fluid is having is effectively contributing into the heat transfer. It is nothing but the ratio of uh, conductive resistance at some place to the convective resistance. You can find it out. And for force convection, what happens that it is a function of two non-dimensional numbers that I have already mentioned, Reynolds number and Prandtl number. So there are some empirical correlation for the what to say theoretical calculations for laminar flow. These are the what we do actually. Directly we don't get the convective heat transfer values. We first calculate Nusselt number, and from Nusselt number we get this convective heat transfer coefficient values, and the thermal conductivity here that we use is the thermal conductivity of the fluid. For a flow across cylinder or cross flow sort of things where there is a cylinder there and field is around, this kind of correlation is used. We can find them in various standard books that are available, and these are the values that have to be taken care of. C and M we need to choose properly to get these values. One very important thing that happens in this convective heat transfer problem, that we need to find certain value. For in case of Reynolds number, we need to find the viscosity of the fluid and density of the fluid, or the kinematic viscosity of the fluid. And in case of Prandtl number, we need the Cp value, we need the K value, or the Prandtl number also. And these are thermophysical properties. So thermophysical properties change with temperature. So while calculating these things, we must know at what temperature we need to take this value. Either we need to take this values at the surface temperature, or we need to take this value at the temperature of the bulk fluid. So what happens when we are doing these values, it is sort of a tradition for some reason, and that is logical also, that we take these uh, these properties at the average temperature, and this average temperature is has a name. It is known as film temperature, at which we take these values. So whenever we are doing these kind of things, we take some sort of an average of the surface we have, and we have some value for the bulk fluid, and we take the average and we take the properties at that temperature. Empirical correlations, for example, in when the flow is turbulent, okay, we have calculated Reynolds number and we have found that okay, the flow is turbulent. So there we have Galinsky's correlation. In various situations, various correlations are used. I just want you to see that which, and these are very prominent ones. These are not uh, uh, very sparsely used. They are very commonly used correlations. These are mostly used in the design of these heat exchangers when flow is happening inside the tube. Usually because the flow is turbulent only, it's very difficult to have a laminar flow. And Dittus-Walter equation is that we will use here, and it is used very frequently. And one very important thing there, one must notice that it is different. This correlation is different when fluid is having cooling or is being heated or being cooled. If the fluid is in such an arrangement that the temperature of the fluid is increased, so there the value of n we will take equal to zero point 0.4, and where it's being cooled we will take it to be zero point 0.3. This Schneider-Tate correlation is although more exact than this Dittus-Boelter, but Dittus-Boelter is very easy for some mathematical reasons. And in the case, in a very special case, when the flow is inside a duct and it's fully developed and it's laminar also, the Nusselt number is a constant. And there are two cases: the constant heat flux condition where the Nusselt number is 4.36. In this case, the heat flux is constant, and in one case where the temperature of the wall is fixed, and there the Nusselt number value is 3.66. The second case is where phase transfer is taking place, because in case of phase transfer the temperature is constant. Applications of force convections are very wide. Even in this image you can find it in very I guess in two places easily you can guess. One is this radiator. We have two radiators here. When car will run at a high speed, this is required. Why? Because the system rejects some amount of heat, and that rejection has to be taken care of. And in heat engines the rejection is of the order of around 70%, also sometime when the efficiency is very less, because these kind of engines have a very good engines might have an efficiency around 50%, or around 50% of heat or more than that is rejected. So this is the rejection. This is rejection in one place. This is using air. And another place what's happening when the crankcase is inside, so there is an enclosure outside there. So where coolant is present, coolant is a liquid that takes heat away from the surroundings of the combustion chamber. So in that way multiple fluids are used. Here air is used as a medium. Inside there is water coolant. So force convection takes place because there is a pump there. In one of these pulleys drives a pump, and that pump flow pushes this fluid all around. So that is one application. Another application is the cooling of your electronic device. If you have ever opened your laptop or your computer, you must find these kind of fan. So what these kind of fan do, along with the usage of heat pipes, that they throw out the excess heat. It's not only the heat engines, electronic chips and electronic circuits also have some sort of losses in terms of heat. So that has to be taken care of. And many companies do this in very fascinating ways. This is trash can from this is macro. You also the known as trash can. They find various type of geometry to doing this. They put fan on the top, creative sort of thing. And if you have a very bad laptop and you cannot do anything, then you can just simply buy a laptop cooling pad. This is also an example of force convection. You put your laptop on it, there is a fan, it will try to. This is a very minimalistic approach and cheap way. And you must think, if that is the case of your laptop, then there are big Google servers and another places how they are cooled. At some point, on some place, force convection plays a role there also. And in industries, for example, the case of that car, what is happening? Two fluids are flowing and the heat transfer is taking place between them. So heat exchangers are the thing that we are talking about. Heat exchanger is, I think, the most uh, right example for this application. And usually the flow inside these and those correlations are used to calculate heat transfer coefficient inside these heat exchangers. And power plants where the boiling is happening. This is an example of a steam generator where these things really are very important. These are all tubes. These are all vertical tubes. The fuel burns over here, it rises over here. There are superheater 1, superheater 2, and it goes back. This is fly ash. And in one point or another there is forced convection happening there. Sometimes there is natural convection also, but usually it's forced convection. See, there is a forced fan. It will take air here and it will push here. and there will be vertical pipes there, water tube pipes. So water will be inside there, and outside the hot air and combustible fluids will go, and they will heat those liquids. I will show you one example. This is a very old sort of boiler, but you can see these vertical tubes inside. These are vertical tubes which will be heated. And when this is a picture of this boiler when it's not under, this is under maintenance, but when things will be burning over here, this fluid will be heated. And I would like to show you how it looks. This is from a small opening. You can see fuel is burning and air is coming inside. How hot it would be there. So this is one application. So how we will measure this heat transfer coefficient? How we will make simple measurements? So there are some assumptions. When the system is in steady state, what we will do, we can electrically generate some sort of heat. And when the system is in a steady state, what will happen? The amount of heat that is coming into the system is the amount of heat that is going out of the system. So we know if we supply current and voltage VI, so the power would be V into I, and that is in watts. And if the heat of the system is not increasing, that it is an indication that it's in a steady state. So the heat we can clearly use this equation to find the average heat transfer coefficient. So this is what we will do for our experiments. For our experiment, what we are having here, and for forced convection, we have a horizontal tube of dia D and the length is L. We have this area. There is a heater that is enclosed, and we are giving power supply, and we can calculate that power supply by measuring the voltage and current. And now what happens when flow takes place due to a blower? We flow air inside, and we have some thermocouples there. So for surface, what we do, we take an average surface temperature. We take these values and we add them, and we divide by 4 to get an average surface temperature. And for the bulk fluid, we take the average temperature by taking average of T1 and T6. Then what we can do, because we know Q, we know area, and we know these two values, so we can easily calculate it. So this is the experimental method, quite simple. Now let's see the laboratory demonstration, and after that I will tell you how to theoretically calculate these things.
Hello students, today we will see the experimental setup which is used to calculate the convective heat transfer for flow inside a pipe. This is our setup. This is our blower. This is connected to a pipe. This is the valve which controls the amount of flow. This is the tube which has heater inside. This tube is heated with heating elements. It has 6 thermocouples lined inside, which have already been shown to you. This is an orifice flow meter. This is used to calculate the flow rate of air inside this tube. These are the differential pressure readings for this orifice meter, and the manometric fluid used here is water. The readings that will be taken from this scale will be in centimeters. This is H1, this is H2. This is our control panel for this setup. From here, when we switch it on, we are getting 3 readings. This shows the current, this shows the voltage, and this indicates the various temperatures. To change temperatures at different locations, we will change this will give temperature at T2 thermocouple, at T3, T4, T5 and T6. So now we will switch on the blower, and this is the dimmer set. This we will use to increase the power that has been given to the heater. Now I will switch on the blower, and now we will increase the amount of current that passes through the heater, and we will increase this voltage to a specific value slowly. So now we have given a set amount of, we have set the voltage here and the current is also fixed. Now after some time, around 20-50 minutes, the temperatures here will take a steady value. You can see that the temperature slowly increases. 26.2, then 26.3, then 26.4, and after some time these readings will become static. Those readings will be provided to you for further calculations.
Please note that from these values we can get value of H1 and H2, and this will be the difference in our reading that is caused due to flow here in the orifice meter. So now calculations. I have made a list of the things that are provided and that will be provided. These are the measured values, the voltage, the current, the heights H1, H2, and the various temperature. Another things have to be calculated at some point or another that I will show you. These are the values that have been given: the density, the length of pipe, the dia of pipe, the dia of orifice, and the coefficient of discharge for that orifice. These values you will have to find from the some data book. You can find these from these kind of tables for various temperatures for calculations. Now, for experimental, I have already told that this is the Q is the heat transfer. You find the area and average surface temperature, average free stream temperature, and then simply you can put in this equation, equivalent sort of equation, and you can get experimental heat transfer coefficient. Now for the theoretical heat transfer coefficient, uh, this is important. So how we will find this? We first have to find Nusselt number, and for Nusselt number, from Nusselt number we can get the value of H. We know this, but we don't know the value of Kf. So how we will find the value of thermal conductivity? So as I already told, we need to find the film temperature. We will find the average of surface and the ambient temperature, and there we will find the Kf values. And now after that, okay, we have found the Kf value also. But now how we will get this? We need to now find the Nusselt number. And we have already seen that Nusselt number is a function of Reynolds number and Prandtl number. So now there are many correlations. Which correlations will we use? How we will use? So first thing we know that okay, this is a pipe flow sort of problem, and the fluid is flowing inside the fluid. And now then we need to find out okay, is will the flow be laminar or is it turbulent? How we will find that out? For that we need to calculate Reynolds number. Reynolds number, we are having only the dia of the pipe. We don't know the velocity, we don't know the kinematic viscosity. So we will try to find out one thing at a time. Kinematic viscosity we can find on the film temperature, and the velocity, how we can find? If we know the discharge and we divide it by area of the pipe, we can get this velocity very easily. And how we will find the discharge? We will use this equation for the orifice flow meter. I will not go into detail of this, but you calculate area, you put in this formula, you will get it. The manometric head here will be calculated in this way because uh, the manometric the calculation, you simply put in this equation, you will get these values are in centimeters, h1 and h2. You will simply get delta h value, you will get the discharge, and then dividing that we will get the velocity, so you can get the Reynolds number. And it's pretty good chance that that Reynolds number is turbulent, and it will turn out that Dittus-Boelter correlation will be used, and that is a very widely used correlation also. And now what's the problem here? We need to find now Prandtl number. So Prandtl number also we will find at the film temperature value, and we will use this thing. You can think about it, the flowing is being heated, so we'll use the n value as zero point 0.4. So what happens now? We have Reynolds number also, we have Prandtl numbers also, we have n also, so we have the Nusselt number. Now when we have the Nusselt number, we can put this Nusselt number into this value, and when we will put there, we will get the convective heat transfer coefficient, the theoretical value. For the deliverables of this experiment, these two values you have to be calculated. maybe at one point or maybe for different readings. That will depend on what kind of data you get. Thank you.